I want to talk about the addition of chlorine and bromine to alkenes. This is an electrophilic addition reaction, but there are a couple of twists to it. To appreciate that, let's first take a look at the standard electrophilic addition mechanism. There are two steps. In the first step, an electrophile, that's something that needs a pair of electrons, reacts with the pi electrons of the alkene. This forms a sigma bond and makes a carbocation intermediate. In the second step, a nucleophile adds to that carbocation. That makes a second sigma bond. This addition takes place by two separate steps with a carbocation intermediate. This carbocation intermediate has an empty p orbital, and the lifetime of the carbocation allows rotation about the carbon-carbon single bond. So there are two conformers that can react with the nucleophile to make product. Nucleophile can add to this p lobe or this one, or in this conformation add to this p lobe or this one. Now notice in the carbocation on the left, substituents 1 and 4 are back, but on the right is substituents 1 and 5. So these two conformations will lead to separate stereoisomers. In addition, the electrophile could add to the bottom of the pi bond, making the carbocation I show at the bottom left, and that can rotate to make another conformation, the one I show at the right, and those two carbocations can react with nucleophiles, the nucleophile adding to either lobe of the empty p orbital. The point is that this standard two-step electrophilic addition mechanism leads to formation of all four possible stereoisomers of product. This reaction mechanism is not stereospecific. Regardless of which stereoisomer we start with in the alkene, we'll end up with all four possible stereoisomers of product. Now let's go to the addition of chlorine and bromine to an alkene. Take a look at the specific example I've shown at the bottom here. Bromine adding to cyclohexene. We only observe formation of the trans 1,2-dibromide. No cis is formed. This reaction is stereoselective, isn't it? Of two possible stereochemistries, cis and trans, we only observe formation of the trans. Compare what we're looking at here to what we see above. In addition to noticing that this reaction is stereoselective, there's no cis isomer. A second question is, where's the electrophile? Well, let's start by looking at bromine, which has to be the electrophile, and understand why it is. Bromine, often written simply as Br2, has two bromine atoms tied together by a sigma bond. I've shown the pair of electrons of that sigma bond in orange at the right. In addition to that pair of electrons, each bromine atom has three other pairs of electrons. It certainly doesn't look like a candidate for being an electrophile, with all those electrons around it already. But take a look at what happens when bromine comes close to a pi bond. When molecular bromine comes close to a pi bond, it becomes polarized. The electrons associated with that molecule move away from the pi bond, moving away from one bromine atom and toward the other. This creates a partial positive charge on the bromine atom that's closest to the pi bond, and that makes it an electrophile. So, odd as it might seem, this pair of pi electrons reacts with the bromine molecule, and that pair of sigma electrons stays with this bromine to make bromide. So that's the first odd thing about addition of bromine and chlorine to a pi bond. The halogen molecule, which appears to have lots of electron density, becomes an electrophile when it's close to a pi bond. The second interesting thing is that the intermediate form is not a carbocation. In the case of bromine, it's what we call a bromonium ion, or if it were chlorine, we'd call it a chloronium ion. The halogen is actually bonded to both carbons, and there's a positive charge on the halogen atom. Notice that this step makes bromide as a byproduct, and that bromide has four pairs of electrons around it. I'm going to draw in one pair of electrons to emphasize that it can be a nucleophile. And that nucleophile has to react with this intermediate from the back side. The bromine that is already there protects the other side from reaction. So the nucleophile can add here, while this bond breaks, or it can add here, while this bond breaks. This makes two different products. They're different because they're stereoisomers. And in fact, they're a pair of enantiomers made in equal amounts. Interestingly, the same pair of enantiomers results if bromine reacts as an electrophile on the other side of the pi bond. I've drawn the pair of electrons between bromines has shifted toward one of the bromines, polarizing the bromine molecule. Reaction of the pi bond electrons with bromine makes a sigma bond and forms an intermediate. That intermediate makes the same product you see above, with the nucleophile adding to this carbon, breaking this bond, or adding to this carbon and breaking this bond. The same two stereoisomers result. Overall, of 4 possible stereoisomers, only 2 are made, a pair of enantiomers in equal amounts. They're a racemic mixture. This reaction is stereoselective. Of 4 possible products, only 2 are made. And it turns out that the stereochemistry of the alkene itself, whether it is E or Z, dictates which 2 stereoisomers are made. Take a look at what happens when we use the other stereoisomer. We've been looking at a reaction that starts with the Z stereoisomer. Let's look at what happens when we have the E stereoisomer. I want you to keep in mind that the products from this reaction were SS and RR stereoisomers. Now we have the E stereoisomer. The pi bond makes a bond to bromine, as those sigma electrons stay with this bromine to make bromide. The bromine is formed and reacts with bromide, reacting either here to break this bond, or here to break this bond. The products that are formed are RS and SR. Recall, from the Z isomer, we made RR and SS. This is the other pair of enantiomers. And you might already be ahead of me. If reaction of bromine comes from the bottom side of the pi bond, we make the same pair of enantiomers. The bromine is formed at the bottom side of the pi bond. When bromide adds, it adds from the top. So that pair of electrons from bromine forms a bond with this carbon, breaking this bond, or this carbon, breaking this bond, making the 2 enantiomers you see above. This type of addition, which accounts for the stereoselectivity, is called anti-addition. Bromine adds from one side, and the other bromine adds from the other side. Put this term in your mind. It's very important and crops up from time to time. And because the stereochemistry of the alkene dictates which 2 stereoisomers we form, which pair of enantiomers, this reaction is also stereospecific. So the take-home is, addition of bromine and chlorine to an alkene puts halogen atoms on adjacent carbons. The reaction takes place with anti-addition, so it's stereoselective, and the double bond stereochemistry dictates which 2 enantiomers we make, which means that this electrophilic addition is stereospecific as well as stereoselective.